When an object is acted on only by the force of gravity, it is in free fall. For instance, I drop a ball. Once it is no longer touching my hand or the table, it is acted on only by the force of gravity, and so it is in free fall. This is true if I drop the ball from rest or if I throw it down at some initial velocity. If I were to throw the ball upwards, once it is no longer touching my hand, on the way up, at the very top of its motion, and on the way down, it is acted on only by the force of gravity, and so it is in free fall. Another example is projectile motion. I throw the ball at an angle with respect to the horizontal. Once it is no longer touching my hand, it is acted on only by the force of gravity, and so it is in free fall. Now, objects are in free fall as long as the drag force or air resistance can be considered to be negligible. And that is true as long as the speeds are not too high and the mass is not too low. It also depends upon the shape of the object. For instance, a piece of paper falling through the air experiences significant drag force, and so it would not be considered to be in free fall. When objects are moving near the surface of the Earth in free fall, they all have the same acceleration, independent of their mass. And that acceleration is given a special symbol g, and it is called the acceleration due to gravity. And it equals 9.8 meters per second squared, and it is directed towards the center of the Earth.
Let's find the acceleration, velocity, and position as functions of time for an object in free fall. And we will find these from the kinematic equations of motion. This dot represents the object. There is one force acting on it, the force of gravity, and the acceleration a is downwards. Let's define a coordinate system. Let's take down as the positive x direction, as shown here. We want to find three graphs: acceleration versus time, velocity versus time, and position versus time. Acceleration versus time is easy. The acceleration is constant. It equals g, the acceleration due to gravity. So we just draw a horizontal line, as shown here, with a value of g, or 9.8 meters per second squared. To find velocity, let's use this kinematic equation. V equals v0 plus at. v0 is the initial velocity, and we'll make that equal to 0. The object was dropped from rest. And the acceleration is g, and so we get v equals gt. Well, that is a linear function with a slope of g, and when t equals 0, v equals 0. So this is the graph. Now let's find the position as a function of time. We'll use this kinematic equation. X equals x0 plus v0t plus 1/2 at squared. x0 is 0. That is the initial position. v0, the initial velocity, is also 0. And a is g. So we get x equals 1/2 gt squared. This is the equation of a parabola. It's a curved function. And when t equals 0, x equals 0. So it looks like this. The slope of the tangent to x versus t is equal to the velocity. When t equals 0, the tangent is horizontal, so it has a slope of 0 corresponding to a velocity of 0. As t increases, the slope of the tangent increases, corresponding to an increase in velocity. This is what we find using theory. Now let's do an experiment.
We have been studying free fall in class, and Giselle is asked to experience free fall for herself. So we are walking over to a bridge now, and when we get there, I'm going to drop her over the edge of the bridge, and she can tell us what free fall feels like. Now, don't worry. I'm all about safety on this channel. There will be a mattress at the bottom to protect her, so she's not going to be injured.
Here's the bridge. Okay, Giselle, there you go. Let's get ready for the drop. It's a long way down. I'm having second thoughts. I don't want to do this anymore. Please. It's perfectly safe. There's nothing to worry about. There's a mattress at the bottom. Remember, this is for science. Okay, I'll do it for science. Great. Here we go. Stop! There's no mattress. Where's the mattress? Oh no! I stopped the video when I did, because I don't want to show what happened when she hit the ground. That's not this channel. This is not a channel where people come to gawk at tragedies. This channel is a safe space for students. Or, well, it wasn't a safe space for Giselle today, but my goal is to make it a safe space for students. I analyzed the video of Giselle falling, and I put a red dot to mark her position as she fell at every second frame, as shown here. The red dot is to the right of Giselle. So we get a series of red dots. This is called a motion diagram. Each dot, successive dots are separated by equal time intervals, the time for 2 frames of the video, and you can see that the distance between neighboring dots increases as she falls. That distance is delta x. The velocity is equal to delta x over delta t. Delta t is always the same, but delta x is increasing as she falls. This means that as Giselle fell, her speed increased. That's what we expect. This is accelerated motion, so she's going to be speeding up as she falls. So I measured the position for each frame of the video, and I had the time, and I was able to draw a graph of position versus time. So here's the position on the vertical axis and time on the horizontal axis. I'm looking at time from 0 to 0.6 seconds. It's not the complete time that she fell. I'm not including the part where she hit the ground. I'm not going to show that on this channel. Here is the experimental data. The blue dots are the position which I measured from the video. This looks like a quadratic function. It's got that curve. So I fit it with a quadratic function, and I got this. It's a very nice fit. So this is what we expected. Position is a quadratic function of time. And the slope of the tangent is equal to the velocity. So when t equals 0, we have a horizontal tangent corresponding to velocity equals 0. And as she fell, as time increased, the slope of the tangent increased, showing that she was speeding up. Here I plot velocity on the vertical axis and time on the horizontal axis. And I'm going from 0.0 to 0.6 seconds as I did for the position graph. Here's what we found. We have a linear graph at the beginning. From 0 to 0.4 seconds, it's linear, corresponding to a constant acceleration. The acceleration is the slope of velocity versus time. But then, the slope of the tangent starts to decrease, and the velocity starts to level out. We have 2 regions here. The first region is the free fall region, where the only force acting, or the only significant force acting, is the force of gravity. In this case, v is proportional to time. But then the acceleration started to decrease, and the velocity started to level out. I think it's going to get to around 5.5 meters per second. To have a decreasing acceleration, there must be an upward force. And that upward force is the drag force Fd. So this is a region of the drag force. The drag force increases when the speed increases. Eventually, the drag force will equal the force of gravity, and then she will fall at zero acceleration and constant speed. To learn more about drag force, see my videos on drag force. I did a best squares fit of the region of free fall. Here's the line of best fit, shown in red. I did the points from 0 to 0.4 seconds. Here's the equation that I got. V equals 10.1 t minus 0.0356. This is a very good fit. R squared was 0.998. This 10.1 in front of the t, that is the slope of the graph. And the slope of v versus t is acceleration. So this 10.1 is the acceleration due to gravity. So the measurement of g was 10.1 meters per second squared. That is 3.1% away from the expected value of 9.8 meters per second squared. In the next section of this video, we will have a time to remember Giselle the Gazelle. You are welcome to skip that section if you want to move ahead with the physics.
Giselle was in my class from 2019 to 2026. 7 years. She came back year after year because she loved the class. She couldn't get enough of it. And she was an incredible student. I thought it fitting that I be joined today by her two closest friends. This is Isabel, Giselle's bestie. And this is Candy. Giselle has been mentoring Candy for over a year. No, I understand. No, I understand. It's okay. Candy has asked that she not be on camera for the rest of this video. She is devastated, as you can imagine. Well, I made some mistakes today, didn't I? I was supposed to put the mattress at the bottom of the bridge. I meant to do it, but I forgot. It was a mistake. A mistake that had tragic consequences. Even worse, when we got to the bridge, Giselle told me that she had second thoughts. It's on the video. She said she didn't want to go through with it. But I didn't listen to her. I dropped her anyways. I should have listened to her. I want to be authentic on this channel. Part of authenticity is to be trustworthy. Giselle put her trust in me today, and I failed her. I was untrustworthy. I would like to take this time to apologize to you, to my subscribers, to Isabel and Candy, to all of Giselle's friends. I am so deeply sorry for what I did. I am devastated. It's all my fault, and I blame myself. One of the goals for this channel is vulnerability. I want to show you when I am vulnerable, and I hope that you can show me when you are vulnerable. I hope that this channel can become a safe space where we can share our vulnerabilities. Today I talked about the mistakes that I made, and how it made me feel, and how it made you feel. That's vulnerability. That's a good thing. So, I don't feel so bad now about what happened to Giselle. In this tragedy, I found my vulnerability. I'm proud of that. I'm happy now. It's all good. In the comments, tell us of a time when you were vulnerable. Let's start the conversation. Now, how can I redeem myself? How can I become truly authentic in this channel? I know. To be truly authentic, I need to show what happened when she hit the ground. I have put it at the end of this video. Believe me, you're gonna want to see it. So, keep watching.
Let's discuss the free fall of Giselle the Gazelle. She fell from a bridge at a height of 5.5 meters above the ground. We will assume that air resistance is negligible in this calculation, although when she actually fell, air resistance was not negligible. But take it to be negligible will simplify our calculations. Here's what we want to find. A. Determine the time to reach the ground. B. Determine her velocity just before she hits the ground. C. Determine the average velocity. And D. Sketch a graph of V versus T and determine the acceleration and displacement from the graph. And then sketch graphs of A versus T and X versus T. Let's set up this problem. The first step is to draw a coordinate axis. So I'm going to take the x-axis. The positive direction is downwards. And Giselle started right here at x equals 0. And then she got to x equals 5.5 meters when she was on the ground. There, she fell to the ground. Let's draw a motion diagram. So we have her initial position, that red dot. She falls for a time interval delta t, gets to here. For the same time interval, she gets here. And then for successive time intervals, here, then here, then here. You can see that the spacing between the dots is increasing as she falls. Delta x is increasing, which means that her speed, her velocity is increasing as she falls, as we saw on the video where I analyzed her position versus time. Now let's define the symbols. x0 is the initial position. It was 0 meters. v0 is the initial velocity. It was 0 meters per second. And t0 equals 0 seconds. That is where we started the clock. Then at the end, x1 is 5.5 meters. That's her final position. v1, her final speed, her final velocity, we don't know. That's what we're trying to find. And t1, the time for her to get to the ground, is also something we don't know. That's what we're going to find. And throughout this, the acceleration is equal to g, and that's 9.8 meters per second squared, and it is directed downwards. Let's solve for the time. Part A, find t1. We can use this kinematic equation. x1 equals x0 plus v0 t1 minus t0 plus 1/2 a t1 minus t0 squared. Now in this equation, I didn't have to include the t0 because it is equal to 0. But I put it here just to show you that in general, you can solve these problems where the initial time is not equal to 0. And so you have to put it into your equation. Now, let's put in the things that we know. First of all, x0 is equal to 0. So that term just cancels out. Also, v0 is equal to 0, so that cancels out. And t0 is equal to 0. So what do we get here? We get x1 is 1/2 gt1 squared, because a is equal to g. And we want to solve this equation for t1. To do that, multiply both sides by 2 and divide both sides by g, and then take the square root. We get this. t1 is square root 2x1 over g. Now let's put in the values that we know. x1 is 5.5, g is 9.8, and we get t1 equals 1.06 seconds. So we got t1 is 1.06 seconds. Now let's look at part B. Let's find the velocity just before she hits the ground. We find v1. Let's use this kinematic equation. v1 equals v0 plus a t1 minus t0. Again, I didn't have to put the t0 in the equation since we started at t0 equals 0 seconds, but in general, you may not be starting at initial time of 0. So I put it in there. Now, what do we know? We know that v0 is 0, t0 is 0, and a is g, and so we get this, v1 is 0 plus g t1 minus 0, or v1 is g t1. Then put in our values. G is 9.8, t1 is 1.06, and we get v1 equals 10.4 meters per second. That's one way to solve the problem. But when we're working with the kinematic equations, there's usually more than one way to solve the problem. So I'm going to show you another way that we could have solved this problem. A different method. Let's find v1 first, and then find t1. So we're going to start with part B and then find part A. You don't have to answer the questions in the order that they give you in the question. Just answer the question in the order that works. Let's look at this kinematic equation. v1 squared is v0 squared plus 2a x1 minus x0. This is the equation that doesn't contain the time. Let's put in the things that we know. Well, we know that initial velocity v0 is equal to 0. That's equal to 0. And x0 is equal to 0. And continuing, we get v1 squared is 0 squared plus 2g, a is g, x1 minus 0, which is v1 equals square root 2g x1. Now let's put in our numbers. G is 9.8. x1 is 5.5. And we finally get v1 equals 10.4 meters per second. So now we've got v1, part B, and now let's find part A, t1. We'll use this equation. v1 equals v0 plus a t1 minus t0. So what do we know here? We know that v1 is equal to 0, so that v0 equals 0, so that cancels out. t0 equals 0, that cancels out, and a is equal to g. And so we get this, v1 is 0 plus g t1 minus 0, or v1 equals g t1. Divide by g, and we get t1 is v1 over g. Putting in the numbers, v1 is 10.4, g is 9.8, and we get t1 equals 1.06 seconds. So using our different method, we got the same result for v1 and t1. Now let's find the average velocity. We have t1, 1.06 seconds. v1 is 10.4 meters per second. Let's find v average. There's two ways we can do it. Method 1, it is only valid for constant acceleration. This problem we had constant acceleration, so we can use this method. In that case, v average is v0 plus v1 over 2. So it's the initial velocity plus the final velocity divided by 2. Put in the numbers. v0 is 0, v1 is 10.4, and we get v average is 5.2 meters per second. Now let's look at method 2. Method 2 is valid no matter what the acceleration is. It doesn't have to be constant. For any acceleration, v average is delta x over delta t. So it's x1 minus x0 over t1 minus t0. Putting in the numbers, it's 5.5 minus 0 over 1.06 minus 0, which gives us 5.2 meters per second. The same as method 1. Velocity and acceleration graphs. Let's draw a graph of velocity versus time. Time goes from 0 to 1.06 seconds. Velocity goes from 0 to 10.4 meters per second. So we know what the first point is. When t is 0, v is 0. So there's our first point. And then our final point. T was 1.06. V was 10.4, right there. And we join these 2 points with a straight line. Because when the acceleration is constant, the velocity is going to be linear. So there's our straight line. So this is our graph of velocity versus time. Now the acceleration is a slope of v versus t. Let's find the slope. Slope is equal to rise over run, or delta v over delta t. Here's the rise, delta v, and here's the run, delta t. And so we're going to get v1 minus v0 over t1 minus t0. So that's going to be 10.4 minus 0 over 1.06 minus 0. Right here, and we finally get 9.8 meters per second squared as we expected. Now let's draw the graph of acceleration versus time. It's very simple. The acceleration is constant. So as we go from 0 to 1.06 second, we have acceleration constant value of 9.8 meters per second squared. So it's just a horizontal line. So there's our graph of acceleration versus time. Now here's a little aside for you. Let's look at the area under the graph of A versus t. When we say area under a graph, we mean the area between the graph and the time axis. If the acceleration is above the time axis, that's a positive area. If it's below the time axis, that's a negative area. This is above the time axis, so it's going to be a positive area. And we want to find the area of this shaded rectangle. Area is length times width. So we have a length here of 1.06 and a width of 9.8. So we get this, multiply them together, you get 10.4 meters per second. 10.4 meters per second. Do you know what that is? The final velocity was 10.4, the initial was 0. So the 10.4 is the change in velocity. So this is the rule. For a graph of A versus t, the area equals the change in velocity. Just like the area under a graph of velocity versus time is equal to the change in position, or the displacement. Let's use that in order to draw our position graph. Here's our graph of velocity versus time that we just found. Displacement is the area under a graph of v versus t. So let's find this shaded area. This is a triangle. The area, which is equal to delta x, the displacement, is 1/2 base times height. This is the base, 1.06 seconds, and this is the height, 10.4 meters per second. Put in these values, we have this. Multiply it together, we get 5.5 meters, which is what we expected, because we know that she fell 5.5 meters. Delta x is x1 minus x0, so that's 5.5 meters. x0 is 0, so x1 must be 5.5 meters. Now we can draw our graph of x versus t. Time goes from 0 to 1.06 seconds. Position goes from 0 to 5.5 meters. We have 2 points. The initial point, t is 0, x is 0, right here. And then the final point, t is 1.06 seconds, x is 5.5 meters, right here. How do we join these 2 points together? It's not a straight line, which it was for velocity. If acceleration is constant, velocity is linear, position is going to be quadratic. So it's going to be a parabola. And it's going to look like this. The slope of the tangent to this position versus time graph is equal to the velocity. So initially the slope has to equal 0, as it is here. It's a horizontal slope initially, corresponding to velocity is 0. As it falls, the slope of the tangent is increasing, corresponding to the increase in velocity. So this is a graph of position versus time. As promised, in the next section, we will see what happened when Giselle hit the ground. So, keep watching. Here's the drop. I slowed down the playback speed to see more clearly what happened. Oh, she hit the ground on all 4 legs. Then she rolls several times. I don't think it's possible to survive that. After I finished the video, I went down there to retrieve her body. I should have put the mattress there. I'm gonna forget. Where is she? Oh, there she is. It doesn't look good. Giselle! Giselle! Are you all right?
I am happy to report that Giselle is alive. Giselle, how did you survive the fall?
I bent my knees when I landed. This increased the time to stop, causing my acceleration to decrease. And if the acceleration decreases, the force of the ground on my body decreases. The result is...
So, it's the force of the ground on your body which causes injury.
That's right.
And if you reduce that force, you reduce your chances for injury.
Correct.
Force equals mass times acceleration. And acceleration is delta V over delta T. So force is mass times delta V over delta T. Now when you're falling, you can't reduce your mass. And delta V is fixed because the final velocity after the crash is always 0 meters per second. You stop at the end of the crash. The only thing you can change is delta T. Giselle, by bending your knees, you increase delta T, causing the force to be decreased. And that saved your life. Giselle, you used your knowledge of physics to save your life. I'm impressed.
I learned it from you. I love this channel, and you're my favorite teacher. You're the GOAT.
Thank you, Giselle. Now, the reason we did the experiment was for you to tell us what free fall feels like. So, how did it feel?
At first, I could feel myself speeding up. It made my stomach churn. Then it felt like I was floating on a cushion of air.
At the beginning, when you were speeding up, that is when you were in free fall. The only significant force acting on you was the force of gravity. But later on, when you felt like you were floating on a cushion of air, that's when the drag force became significant. And in fact, at that point, the drag force equaled the force of gravity. So the net force was 0 and your acceleration was 0. So you were moving downwards at a constant velocity. That velocity is called the terminal velocity. For more information, see the playlist on drag force.
Here's a summary of what we learned today. Free fall. An object acted on by only one force, the force of gravity, is in free fall. Air resistance or drag force must be negligible for the object to be in free fall. Near the surface of the Earth, the acceleration of an object in free fall is constant and equal in magnitude to the acceleration due to gravity. So A equals G equals 9.8 meters per second squared. And objects in free fall include those dropped from rest and those thrown upwards, downwards, or at an angle with respect to the vertical. Theory. Graphs of acceleration, velocity, and position for an object in free fall were calculated using the kinematic equations of motion. The object was dropped from rest, and the x-axis was positive going downwards, and we started at x equals 0. For acceleration, it's a constant, a equals g, the acceleration due to gravity. So in the graph of a versus t, we just have a horizontal line at acceleration equal g. Velocity, v equals gt, that's the linear function. So we got the straight line as shown here with a slope equal to g in our graph of v versus t. Position, x equals 1/2 gt squared. The graph looks like this. It's a parabola, starting at x equals 0 when t equals 0. Here's some more about the graphs. The slope of velocity versus time is acceleration. So this is the velocity that we calculated for Giselle, assuming that there is no air resistance. And if you take the slope of that graph, slope is rise over run, we get 9.8 meters per second squared. That's the acceleration due to gravity. The slope of the tangent to position versus time is velocity. Here's a graph which we determined for position versus time. And if you take the slope of the tangent to this graph, you'll see that it equals velocity. So right here in t equals 0, the tangent is horizontal, corresponding to the slope of 0 and velocity of 0, as shown here. And then as time increases, the slope of the tangent increases, corresponding to an increase in velocity. More about the graphs. The area under velocity versus time is change in position. When we say area under a graph, we mean the area between the graph and the time axis. If velocity is above the time axis, that's a positive area. If it's below the time axis, that's a negative area. So here's our graph of velocity versus time for Giselle, assuming no air resistance. And the area under this graph, it's a triangle, 1/2 base times height. And we got 5.5 meters. And that was her change in position, or the displacement. She started at x equals 0, and she ended at x equals 5.5 meters. The area under acceleration versus time is change in velocity. So here's the graph of acceleration versus time. The area is just the length, 1.06, times the width, 9.8, and we got 10.4 meters per second. That's the change in her velocity. So she started at velocity equals 0, and she ended at velocity equals 10.4 meters per second. Experiment. When Giselle was dropped from the bridge, the graph of velocity versus time did not match the theory because there was significant drag force. Here's the graph which we had. So in this region here, from time of 0 to 0.4 seconds, that is a free fall region, and the only significant force acting was the force of gravity. So this is a linear graph as we expected for an object in free fall. But then the slope of the graph starts to change, and the velocity seems to be leveling out to a constant value. This is the drag force region. As the velocity increased, the drag force increased, and eventually it was no longer negligible. So now we had to include the drag force also acting on the object. So these two forces cause the net force to decrease, causing a decrease in the acceleration. And you can see the slope of the tangent is decreasing here. Eventually, the acceleration will become 0, and the object will move at its terminal velocity. Measurement of g. We determined the acceleration due to gravity by finding the slope of the graph of v versus t when the object was in the free fall region. We did a line of best fit, and this is what we got. V equals 10.1 t minus 0.0356. the coefficient of t, 10.1, that is the slope of the line. And that is equal to the acceleration. And so we found that g, the acceleration, was 10.1 meters per second squared. That's very close to the expected value of 9.8 meters per second squared. Problem solving. When we solve problems in kinematics, it is very important to start with a pictorial representation, showing the coordinate system and all the given and unknown values. So in our problem of the falling Giselle, we drew the coordinate axis, the x-axis going downwards. She started up here at x equals 0. Then she fell and got to the ground at x equals 5.5 meters. I drew a motion diagram to help us understand what's going on. This is accelerated motion. So these dots are at equally spaced time intervals, and the distance between the dots is increasing, showing that she is speeding up as she falls. This is accelerated motion. And then we write down all the unknown values and the known values. So up here at x equals 0, we have the position, velocity, and time. And down at the end, we had the position and the two unknowns, v1 and t1. Those are what we are trying to find. And throughout, we had the acceleration of 9.8 meters per second squared down. So now, right here, we have everything we need to solve the problem. Then we use the kinematic equations to solve the problem. And so we look at our kinematic equations to see what we can do. And there are many different ways to solve the problem. We want to find v1. Well, looking at everything we have here, we could use this equation. We know everything on the right side of this equation. We could get v1 there. And then to get t1, use this equation. Or we could find t1 first. We could use this equation. We know everything on the right side. We know everything in this equation except the time. And that will give us t1. And then once we get t1, we put it into this equation to get v. So there are many different ways to solve problems when you use the kinematic equations. Thank you very much for your attention during this presentation. Giselle, Candy, Isabel, and I really appreciate you viewing our presentations, and we hope you come again soon. Please be sure to like and subscribe, and check out the playlist on drag force, and watch the next video. See you next time. Bye.